We have already covered some methods of machine learning, and we have covered some methods of supervised machine learning, and now we are continuing with methods of unsupervised machine learning. And today we will be considering a method called Gaussian mixture model, or GMM for short. This is a method that I guess is a little bit hard to understand because of quite heavy formulas. It's hard to understand, let's say, from a formal point of view. But on the other hand, it's quite intuitive if we consider this method just from, let's say, hand-waving point of view. So I will try to give you first of all, the hand-waving point of view. So we will consider some sort of intuitive ideas that stand behind the method of GMM. And I will show you just briefly some equations and some formulas just because they are quite heavy. And I don't think it's that we should focus on them so hard. So what is GMM for? First of all, we will try to understand incrementally such things about GMM. So what is a mixture model and why do we use that? So what do we want from that mixture model? And the answer will be quite interesting. The previous lecture, we considered methods of clusterization. We can use GMM for clusterization, but it will turn out that GMM is much better in something different. We will use that as a generative model. The first question for you is just whether you remember what is the generative machine learning model. What does it do for us, and what is the different kind of models that we have? So I'm solving some, let's say, classification problem. Yes, we can generate some new entries based on the data that we have in our data set. And we can do that thanks to what? So what additional information does it give to us that we can use for generation our new data? If we have just a discriminative model, we can expect from that I'm giving some point to that model, and the model discriminates to which class these points should belong. So it's just classifying the point, nothing more. When I'm dealing with generative models, I have some additional information. My generative model is trying to recover somehow the information on the underlying distribution, probability distribution, that all my data points come from. So any data set that I'm working with, I can consider as some sort of points that came to me from some sort of random distribution. So I have a random distribution somewhere out there, and it generates for me my points into my data set. And with the help of the generative models, I'm trying to recover some information on that distribution. So if I have some ideas, maybe that distribution can be some Gaussian distribution, maybe something else. So that depends on the problem that I have. But a generative model will try to recover that distribution for me. And you might already guess that GMM is the generative model that will try to recover for me some sort of distribution that contains Gaussians. So it's some sort of mixture of Gaussians. So you might already guess that. Okay. Of course, generative models are a bit more complicated than just discriminating models, well, as a rule, let's say, and they need from me some assumption about that functions that I'm feeding. Because you know that we always have a finite data set. So the number of points in the data set is always finite. So I cannot just go all over all possible distributions, because there are too many functions that I can use to generate the points. So probably I need some assumptions. So I'm taking some family of distributions. In this case, I'll be taking some mixture of Gaussians. And then I do some process that chooses from that family the best one, the best suited distribution that could have generated the points that I have. So this is the problem. We will consider that in a moment, just in a little bit more details, but that's the general idea. So I will show you even, I guess, some example of generating some new points with the GMM at the end of the lecture. But okay, we'll get to that. What else? I will show you some techniques. How can we fit that mixture model? I will show you the MLE approach and the expectation maximization technique. And I will show you that we can cluster our points with the GMM. In some cases, it even works better than k-means that I have showed to you. But I want you to remember that the primary goal of the GMM is basically to be a generative model. So it will be better than k-means, but it still will be not so good as, for example, some spectral clustering or something like that. But that is a generative model, so different ways of clustering, they won't do that for you, while GMM can generate some new points for you, and that's really good. Okay, let's get to the problem. Suppose I have some discrete random variable z, and this v has a support like numbers from 1 to k, and I have a family of distributions pk. So I'm trying to create right now some sort of mixture model. So I will generate a number with this z, and depending on that number, I will get some point from one of the distributions of the family pk. And that will give me a point into my data set. I guess I should draw that on a whiteboard. So let me do that in more, let's say, graphical representation. So consider for a moment some sort of device. So this device has, let's say, n outputs. Each of them can be activated with some probability. So I have some probabilities, let's say pi1, pi2, and so on up to pi(n). Each output of the device is connected to some different device that can generate random points. But each of the devices to which this one is connected has a different probability distribution inside. Let's suppose that's some sort of normal distribution, so like nothing very fancy. So I have let's say this one, so I have different distributions for each of these devices. Now, when this device activates one of them, it generates me a point it generates me a point following the distribution it has inside. So this is predefined. I have predefined all these distributions, and I get some point from them. And all these points are collected together into one bucket. So suppose I'm collecting them into one big bucket. And when these points are collected, so I got some point in here, in here, in here, I don't know, somewhere here, and so on and so forth. I can somehow recover the overall distribution for these points, and I will get, I don't know, something, let's say, like this. So I have some different distributions for these points. But they all were generated with these devices, each having some simple distribution like a normal distribution. So this will be our model, basically. So we will be considering our data set as generating in this sort of way. So we had some, let's say, device that chose with different different probabilities some sort of different devices, and they have generated points for us. This can be a very practical thing, basically. It sounds, let's say, quite abstract, but if you think for a moment, you can guess that in practice, we quite often have the situation where our points can be considered as coming from two different sources or having quite different properties. And depending on that properties, they may be subjects to different distributions. So that's why we can consider them as some sort of mixed case. So we have some mix of distributions, and we want them, for example, unmix somehow. So we may want to know that, or to have that ability to unmix them. And there may be simplest example. So suppose you are measuring height of people. And if you are trying to fit everyone into one normal distribution, you won't get a very nice result. I guess I even have some picture somewhere in the lecture, so we will probably get to that picture. But let's say you won't have very nice fit for that points. But if you consider, for example, separately men and women, you will get two quite nice normal distributions. So if you are just measuring heights and you don't have the information who were you measuring, you won't get a nice fit because you have something more close to a sum of two normal distributions than just one normal distribution. If you are measuring, for example, velocities of particles somewhere in a plasma, for example, it may be the case that you are just considering velocities of the particles, but you don't know what is the nature of the particle, which velocity you have measured. And you know probably that in plasma, for example, we have at least ions and electrons, and they have a very different mass. So if you think about, for example, a Maxwell's distribution, you cannot have one normal distribution for them both, because they have a very different mass and their distributions are quite different. So that's why you will probably want to consider them as a mixture of two Maxwell's distributions. So one for electrons and one, for example, for ions, and so on. So there may be many cases when you want to consider something like a mixture, and when you probably may want to unmix that. So having some data on that particles, you may try to construct some sort of device that takes that and tries to unmix them and predict this was a detect of an electron, that was a detect of an ion, and so on and so forth. So that's what we will be aiming for today. We will consider a mechanism to unmix this sort of mixture. Okay, so now probably these formulae should be more or less clear. So these pk that were distributions generated for me by my different devices, and these pi k were the probabilities of activating one of the devices. And here is, of course, the overall probability distribution function that we have. One more way to look at the problem. So here is a picture for you. You can think about that random variable k acting like a tag that conditions the probability distribution we use to generate specific point on the second step. So the role of z is close to that of the cluster label. That's why we will later try to use GMM for clustering, and in some cases it works more or less nicely. After the point is generated, the tag is erased, and it makes us impossible to say exactly from which distribution each point came from. But anyway, we will try to guess that. Let's say make some sort of guesstimate. So here are the points with tags, and here are the points with all that labels removed. And here is the picture that shows you the process in one more hand-waving way. Here is some sort of bag with labels, and we are getting one of the labels at random. Of course, depending on the number of that labels in the bag, you will have different probabilities of getting each label. If you have many labels number 1 and not so many, let's say, with number 2, you will, of course, get different probabilities of getting 1 of 2 or 2 out of there. And when you have got that label, you are choosing one of these probability distributions. So with the label 0 or 1 or 2, so whatever you have gotten from that bag, and then you generate a point with that distribution, and you erase the tag, so we don't know from which distribution it came from. This pxi theta k is the same as xi, and at the condition of zi equals to k, it's the conditional probability to get xi if we generate a tag k in the first step. The marginal distribution, if we average over all possible results obtained at the first step, reads as this, a pxi, and you are trying to marginalize with the respect of all labels. So I'm trying to get all different labels k, and I'm adding the probabilities of getting my point xi with respect to any possible label. So here we have the formulae. Why am I doing this all marginalization and so on? We are getting closer and closer to some sort of expressing our equations and getting to the algorithm of estimating where did these points come from and how do our distributions look like. For example, if I have some point on the plane, I know that it was generated, and I want to have some sort of measure how likely could this point occur on the plane. This question should not be strange for you, because previously we have studied so-called MLE from statistics, and you know that when we were doing MLE, we were concerned with the probabilities of getting points somewhere, or let's say not probabilities, but likelihoods of getting points somewhere in our space. And with having that values, so how probable are their appearances at that specific points, we were trying to estimate the parameters of the distribution that we have. And here we will try to do something quite similar. The first question, if I have some point somewhere, I'm trying to guess, so how likely was it to get this point right there? And since I could have gotten this point from any of the k distributions, I'm just trying to take them all into account. So I'm taking the probability of choosing that distribution multiplied by the probability of getting the point from that exact distribution and adding everything together. So that's what I have. We can reverse the problem and ask what is the probability that given point had a tag k. This is called probability membership or responsibility and could be found using a Bayesian theorem. Here is an expression. So this is AIK. This AIK is very similar to the AIK that we had in k-means method. But if you remember, what was the meaning of this parameter AIK when we were considering k-means? Can you recall something from that lecture? So let me help you a bit. AIK in here is very similar to what we had there. And here I define it as the probability of label of this point to be k. So I have a point somewhere, and I'm asking myself, what is the probability that this point was generated with the first distribution? So for example, with the normal distribution number 1 that I have. Then I ask, what is the probability that I have generated it with the second distribution or with the third distribution and so on. So I have these different AIK. And these are some numbers. And I had something very similar when I was considering k-means. So no one remembers, yeah? Okay. That were the parameters that were prescribing our points to clusters. And that parameters AIK in there, in k-means, they could have only values. Maybe anyone remembers which values could they have? Yes, 1 and 0. So we are either prescribing a point to some cluster or we are not. So that was very definite. We were prescribing points to different clusters, and that was all. So this point belongs to cluster number 1, and it will belong there. Here we have some probabilities. So each point belongs to different distributions. And at this point, you might probably guess, how do I want to use this method, for example, for clusterization? So what will I consider as clusters in this case?
Those groups of points that have the highest probability of having the same label.
Yes, I will consider that labels like the method to clusterize my points. So now I get the problem is more or less getting to be more and more clear. So I have some points in some space. So I have many, many data points. And I have a mixture model. This mixture model contains different probability distributions. Each of these probability distributions, like the devices on the whiteboard, I'm considering like some sort of clusters. And I'm trying to guess which point came from which of them, and that will be my method to clusterize them. So I will consider that probabilities, and I will say, well, this point has a very high probability to belong to some of that distribution, so it maybe was generated with that device, and that's why I will consider it as belonging to the cluster of that distribution. So that's why this will be considered as a method of clusterization. Okay. So these things are getting more and more complicated, but anyway. Here is my probability. We notice now that if k-means had very definite AIK, so 0 or 1 only, here we have some sort of fuzzy clustering. So you may not only take, I don't know, the biggest probability of, well, if you consider some point, you can consider all the probabilities that it belongs to each of the k clusters, and you can choose, of course, the one with the highest probability. But you don't only have that, you have the probabilities of this point belonging to each cluster. So this is some sort of fuzzy clustering. And probably you will see some different methods in the future that clusterize points, not like definitely prescribing them to some clusters, but giving them a set of probabilities that this point may belong to cluster number 1 with probability, let's say 90%, to cluster number 2 with probability 10%, and so on and so forth. That's called fuzzy clustering, and probably you will see some more methods in the future that perform that fuzzy clustering. GMM is just one of that methods. Okay, so I want to have that probabilities. I want to prescribe them to my points, but of course I don't have the expression for this P, and I should get it from somewhere. And where can I get it if we think for a moment? Looking at the next formula, can you guess what is this? So what is this formula in its essence?
It's look like bias.
Yes, that's bias. So that's one of our previous lectures. We recall that if I have something like this, some probability with some condition, and I don't like the order, it's more easy for me to get, if I have that probability and condition the other way around, I can do that with bias formula. And here is an example of using that bias formula. So here I'm reversing the order. Now this is P of getting xi when vi is equal to k. And this probability is very easy to get. Why? So what is this Pxi vi equals k? This is the case distribution in my mixture model, yes? I had that k devices, so I take the device number k, I'm looking into there, and there is some probability distribution. And of course, if I have a point xi, I can just plug it into that distribution and get p out of there. So it's not a problem to get this, because when I define my mixture model, I define what distributions do I have in there. So if parameters of my distributions are defined, it's quite easy for me just to plug a point into there and to get some value, some number. So it's nothing hard to get these value, because I have them, I define them when defining the problem. This is the probability of getting some label of that class K. That's my probability pi. So here you see that. So that's defined as well, at least at this point. And we need to divide by this sort of thing. So it's easy to get this thing as well. So this is the overall probability of getting a point at the coordinate xi. So that's okay as well. Here I'm just using bias theorem, and I'm getting this sort of expression. Okay, so direct versus the inverse problem. Direct problem is very easy. I have my probability distributions. I have the probabilities of getting different labels, and I need just to generate my points. Very easy. The inverse problem is much more complicated. I need to estimate somehow for the parameters And that may be quite complicated when I'm having just a data set, because I don't have any labels, I don't have anything. So that may be a problem. Okay, so we will see some methods how to do that. I know that will be maybe a little bit heavy to get through all these formulae, but we will try to do that. Okay, recalling, so what is a normal distribution? Hopefully anyone remembers these formulae. Nothing very complicated here. Just a nice picture for you, how it looks like. I can change the parameters mu and sigma and get different distributions. You see the histogram here. Depending on the number of points that I use, it is more or less similar to the distribution that I expect. So that basically depends on the number of points that I have. Without it, everything looks quite nicely, smooth and nice. Multivariate Gaussian. If we have a normal distribution in the multidimensional space, and most cases we will be concerned with the distributions in multidimensional spaces, because who will want a data set with just one feature? Yeah, so we will have probably many features. And here is the case, how it looks like. So we have a Pn. Here are some parameters. So here is my point x, and these are the parameters of the distribution mu and sigma. Now sigma is the matrix. So that's a matrix, and we will need, if we want to recover the parameters of the distribution, we will need to recover the whole matrix, and mu now is a vector. So it's not like anything changed very much, but this is what we have.
Also x is vector, yeah?
Yes, and x is vector as well, because right now we are getting to a multidimensional space. Here with this sort of sign, I am defining a determinant of the matrix sigma. So it's just a determinant. Mu you can consider as a sort of mean value, some mean vector, and sigma is called a covariance matrix. So that's what we have. Okay, so here are some estimates for mu and for sigma if we have some points generated with that distribution. So that's quite simple. Here is an example of 2D case. Here is my multidimensional normal distribution. Here you see marginal distributions. So it's like I have taken everything that integrated. So I take these points, and you can think about them like I'm making them to fall on that plane in there, and then I draw a histogram in that plane, and that will be my marginal distribution. So that's what I have. Okay, here are the mixtures. So the mixture of the univariate normal distributions, here it is. I have some sum of pi I with normal distributions. Here is my univariate normal distribution, just one-dimensional case. Everything is quite simple. And here is the example I was telling you about. Here is some sort of height distribution for people. And you see that if I am considering like everyone together, so I'm getting everyone into one bucket, and I'm trying to draw some sort of distribution of heights. So here is some height, and here is the probability distribution function of having the height. And you see that it doesn't look very much like a normal distribution, so this black curve. But if I consider that as a mix, yes, please.
It looks is kind of skewed.
Yeah, it's really it's not symmetric. We know that normal distribution should be symmetric, and here is some quite evident symmetry in this curve, and probably it's not a normal distribution. So you cannot fit that points with a normal distribution. It doesn't work like that. But if you consider that as a mixture model, And for example, you will consider men separately and women separately, and then you will draw some lines for them. You will see that they look much more like normal distributions. So it has much more sense, at least in this case, to consider everything as a mixture model, not just like some one curve and one normal distribution. So with two normal distributions, you might get much better results. And probably you can think about some different examples when you can treat your data as coming from some different sources or measured with some, I don't know, different entities, and you want somehow to use that information, to use that fact to get some better results. So like an example with particles, if you have a plasma, you have electrons there, you have ions there, they have very different masses, and probably you won't be considering them as fitting into one normal distribution, but you will probably want to consider them separately, like two normal distributions. Here is one more example. This is a Gaussian mixture in image segmentation. So here are some sort of colors in the image. They were all collected, and we are trying to separate them, to prescribe different points basing on their colors. This is some sort of grayscale image, and you have this range from 0 to, it should be to 256 or something like that. But anyway, we can consider that as a mixture model, and we can try to use that information to somehow segment the image. I'm not sure if anyone uses this approach today, because we have some much more powerful approaches like neural networks and so on and so forth. But in some olden days, people tried to use these sort of models, and they were somehow working. So maybe you will find some usage for them as well somewhere. I don't know. Here is one more example for you. This is a mixture model of 3 normal distributions. And what I want you to show with this model, what kind of distributions can we get if we mix some Gaussians. Here is the example. I can change their parameters. And here are basically my pi I. I can change them as well. And depending on that, how I change my pi, you see that I'm sort of rebalancing these normal distributions. For example, I can just remove one of them and work with 2 distributions. Why not? So here is sort of example like in previous image. So if I have 2 distributions, for example, the probability of getting point from each of them is like 50-50, and you have some different parameters for them, you can see that you might have quite different mixtures. So this sort of line, it's a mixture, and these points on the x-axis, it's some sort of data set that was drawn from their mixture. So you can see how data sets change, and you can see how different can be the functions that you get when you mix these models. So when you have some case that you would like to fit with the normal distribution, but it doesn't work because it's like somehow skewed, it looks not symmetric, and so on and so forth, you might want to consider that is a mixture of 2 normal distributions. Maybe that will help you to get some better results. Why not? This is the case of multivariate normal distribution. Everything is almost the same, but once again, we get our x's to be vectors, we get our mu to be vectors, and we get our sigmas to be matrices. So that's what we have. Okay. So now we have posed our problem, and we will try to get some insights in how can we at least try to solve that. So what will be our problem? So once again, we have some data set. we want to consider that data set as coming from some random distribution, as generated with some random distribution. And we want to consider that random distribution as a mixture of some more simple distributions. In this case, we are interested in GMM, so that should be a mix of normal distributions. So once again, recalling the picture I have shown you, you have some device that with the probability pi chooses one of the, let's say, sub-devices, and that sub-device generates for you a point basing on some internal parameters of the normal distribution that it has. And now we want to unmix that points and to guess, having our data set, which point came from which of the distributions. And moreover, we want even more, we want to guess parameters of that distributions. So that's a very complicated goal, but we can achieve that. What are we trying to do? Here is an example of GMM via the MLE, so maximum likelihood estimation. Let's first recall, hopefully you remember, so what is MLE, so how it worked. Can you recall that?
Likelihood function?
Yes, so we were trying to get the likelihood function, and then we were trying to maximize that. So who remembers how did we get that likelihood function? In some very simple case. Okay, so let me...
Join density of the distribution.
Yes, so we were having some guess for our distribution function, and we were getting the values of that distribution function, like that densities, and we were multiplying them. And that was our likelihood of getting some data set of points. So let me draw that, as I want you to recall that thing. Maybe I would draw it somewhere in here. But my MLE is basically what I'm making a guess. So maybe they were generated with normal distribution like this. Maybe they were generated with normal. So this is my guess 1. Maybe they were generated with something like this. That's my guess 2. Or maybe something like this. My guess 3. And what I was basically doing, I was trying to take these points up to the distribution. I was taking the values and I was multiplying them to get the likelihood. And you probably recall that sort of hand-waving method when I am trying different normal distributions and I have these points. So points are more densely generated near the maximum of the distribution. So if I'm trying different versions of that normal distribution, I would like to have my maximum or closer to the area of the in which these points are the most dense, because I will have, when I'm multiplying these values, I will get some bigger numbers. So that's how it worked. And we will do something quite similar now. Of course, you can write that analytically, you can do all that derivatives, so on and so forth, and you can show exactly that works and so on and so forth. But like hand-wavingly, you can think about this function like you are moving that here and there. You are trying different cases, like you're trying this one, normal distribution, this one, that one, and you are trying to get some likelihood of these points. And why was I able to multiply all these values? Does anyone recall that?
Because we assume that sample is drawn independently?
Yes, absolutely correct. IID, independent, identically distributed. So identically distributed, they come from the same distribution, and independent, they were drawn independently. So that's why I could multiply these sort of numbers to get my overall likelihood. So that was the case. And we will reuse the same ideas in this lecture as well. So we will reuse basically the same ideas of the MLE to get the result. Okay. So now what do we have? So now we aim to estimate the parameters of GML. So my theta. These are basically pi k, mu k, and sigma k. Now let's do what? So we need a likelihood function. The likelihood function is this, well, scary looking expression. What is this expression? We have the probability pi ka, that's the probability of choosing one of the devices, and we have a normal distribution in that device. It has its own parameters, so each device has a normal distribution, but they differ in parameters. So device number 1 has mu1 and sigma 1, device number 2 has mu2 and sigma 2, and so on. And when I have chosen the device, I'm generating a point with that exact distribution. This sum, is basically what? This is my mixture, yes? I'm mixing the distributions of all devices. And this
The density.
multiplication, yeah, so these are the densities, and I'm mixing them together to get the overall probability density function. And this multiplication, it's the same thing that we have done in MLE. So I am multiplying all these densities to get the overall likelihood. I'm multiplying with respect to all the points. So I'm going through each of the points xi in my data set, and I'm multiplying them. Now I can write the logarithm of all these things. We really like to take logarithm when we were doing MLE, because when we have some normal distribution, it's exponent and so on and so forth. In this case, it's a bit more complicated than when we have just one normal distribution. Yes, this product, it becomes a sum. It's much better. So it's easier to work with sum than with, let's say, with the product. But here we have a problem. When we had just one normal distribution, I could have taken that logarithm and get rid of the exponents and so on and get some nicely looking expressions. Now I have the sum under the logarithm, and I cannot do any further transformations of that. And that makes my problem a bit, let's say, complicated. Yes, I can still take some derivatives and try to calculate something, but at the end of the day, you might guess that we will get some equations that we most probably we cannot handle. So that's a bit of a problem. But anyway, we will try to do something. And the solution comes very similar to the problem we had when we were considering k-means. if you remember, in k-means, we had a very similar situation when we couldn't have our parameters a, I, k, and some different things. We couldn't have them simultaneously, and we were continuously updating some parameters, then some other parameters, so on and so forth. So this is one of the strategies. So we separate the parameters that we want to have into, let's say, two different categories, and we are updating them first category number 1, then number 2, number 1, then number 2, and so on. And we will do very similar thing in here. So we will update the parameters of our distributions, and then we will update the table of probabilities basing on that parameters. Then updated this table, we will try to update our parameters and so on in a hope that everything converges and we get some meaningful result. Okay, so how do we do that update? So here is the case. We have our likelihood L, and we are trying to make all that derivatives. I don't think I will get into details of doing that, just because you can take that derivatives on your own. I just want to show you this interesting property that when we are doing all that derivatives of our likelihood with respect, for example, to mu, you get these parameters a, I, k multiplied by some parameters of our distributions. That's a really nice property that comes from deriving the exponent. So when you are searching for the derivative of the exponent, you basically get the same exponent that you had times some derivative of whatever you were exponentiating. So this is basically the case. And this is very nice because this part of the sum is basically aik. And at the moment when you are searching for the parameters of the distributions, you can think about aik as some sort of fixed values. So we will be doing these iterative updates, and we will think at some point, we will think, let's suppose I have aik, and I'm estimating my parameter theta, parameters of all my distributions. Then I will say, okay, I have parameter theta, let me estimate aik. So estimating aik will be quite easy because we have already written the formula for aik. You saw that. Now we should, let's say, solve the problem of estimating parameters theta. So let's do that. So taking derivative, having this expression. Nice. What now? So we can write the value of mu k in terms of aik. Here it is. So we set this equal to 0, we solve for mu k, and so on. So here is the result. Very simple. You can just basically, if you have aik, xi, of course, you have that your data set, you just plug everything in, you get the result. Very well. Sigma k, you do basically the same thing, and you have this sort of expression. So once again, it's really nice to deal with exponents. When you are doing all that derivatives, you are getting basically the same that you had at the beginning. So that's very convenient. So here is the expression you have. And pi k's are a little bit more complicated. The problem is that pi k should all sum up to 1. So we should use this sort of condition, and we do that with taking into account the Lagrange multiplier. So here will be our expression for that likelihood. Once again, we do all that derivatives, and at the end of the day, we get an expression for pi k. So here it is. So hopefully you all can do that calculations if you ever need. It's just taking derivatives from basically exponents, so there's nothing complicated in there. So it may take some time because too many indices, quotients and so on, but there is nothing complicated to that, just time-consuming. And all in all, you will get these sort of expressions. So what I want you to see here, that when I'm calculating, for example, mu k, the only thing I need to make that calculation are these a, I, k. So if for some reason I have a table that prescribes me different points to different distributions with some sort of probabilities, so I'm saying the point number 1 has 90% probability of being from the distribution number 1 and has 5% probability of being from distribution number 2, so on and so forth. So this is enough to calculate my mu k, because xi I have, that's my data set. If I have mu k and aik, that's enough to calculate the sigmas. So here is the formula, and you see that there is nothing more to that. My data set, my mu k that I already have, and aik. And when I have them, I can calculate pi k. I just need aik and the number of points, nothing more. So everything looks quite simple. And when I have these parameters, that's this part. I had aik, and I have updated my parameters of my distributions. So all distributions get their parameters updated after I have calculated this thing. So I do that for each k, for distribution number 1, number 2, number 3, so on. I get them updated. If I have them, I can update my aik. So I can get the other way around and do this turn. So aik, I take them, I recall what is their meaning. So aik is the probability for the point xi to come from some distribution k, and I can calculate that with the bias formula. So that's what I have. And just updating that, I hope that it will converge and give me some more or less nice result. Here is this GMM algorithm written in some more algorithmic style. So what do I need to do that, to perform the GMM? I have data set. I need to initialize somehow my parameters, because you know that we have this problem of egg and chicken. So I need to update A's, I need to update parameters, so I should start somewhere. So either I take some guess for aik, or I take some guess for parameters. So it's more natural, of course, to take some guess for parameters. So in doing that guess, I'm setting some sort of parameters. By any means, how do I do that? Then what do I do the next? Until convergence, I set the responsibility aik, because I have guessed my parameters, I can get aik. I have aik, okay, I update parameters, and then I return. And I do that more and more and more. So that's how our algorithm works. So now let me try to show you some sort of example. Here are my points, and I'm guessing some clusters. So I might guess, let's say, not 3, but 2. I'll try to guess some parameters. Let's do this way, this one this way. And I'm asking my algorithm to clusterize everything. Now you see what happened. So these are the steps that algorithm was performing. So let's see how that works. Okay, so here is my step number 1. What do I do here? So I have some initial guess for the parameters of my Gaussian functions. So this is my initial guess. I have they have some centers, they have some sigma matrix, so on and so forth. When having that guess, I can calculate for each point the probability to belong to each of these normal distributions. Here in the picture, I'm connecting with lines points to that distribution where its probability is higher. But of course, in calculation, both numbers take part. So here is the 3D. Yeah, so I have two distributions, and I'm trying these points prescribe them to one of the distributions. So what's next? I had parameters. I have calculated these A, I, K. I update my parameters. You see that one center has jumped in here into this cluster of points. So that they had a higher probability to belong to this distribution, and then jumped to there. So it's really has some logic. This one has jumped to the center of mass, but you see some sort of points are far away from this center. So probably we might guess that next steps will make this distribution somehow different, and these points will go to this cluster. Okay, so once again, I have updated my AIK, and now I'm updating parameters. And you see that parameters have updated. So this distribution is getting broader. And this one will need to go away from these points. So one more step. Now these points do not belong to this distribution anymore. So the next step should throw the center somewhere closer to this cluster of points. So let's see that. So here is getting closer and closer, and here it converges. So here is the final result that we have. Having that distribution, of course, we can perform some sort of clusterization problem or something like that. We can draw some line of separation between these distributions where one is higher or the other one is higher, and perform some sort of classification if you wish, and so on and so forth. But of course, the most interesting thing for us will be the fact that we have these parameters of these distributions, and if we ever need, we will generate some additional points for us. So if we ever want to have some bigger data set, to have something more, we can generate some points using these distributions. Okay. Hopefully, you will play around with this sort of demo and get some intuitive ideas of how everything works with all these things. Okay. How much time do we have before break? 7 minutes. Oh. Okay. I guess. Okay, I guess I will skip most of the formulae because it's really, I know it's really hard to get grasp of all that things, like just looking at them. So probably you will need to think about them a bit later. I will just show you, let's say, I will just present you some ideas behind that formulae, and that will be okay. And then we will go to break. And after break, I will show you some more practical examples of using all these things. So one more approach to understanding what we are doing in that GMM is so-called expectation maximization theory. Suppose you aim to minimize a likelihood function like this, L, theta, and x. So you have a data set, you have some sort of parameters theta, and so on. Then you can perform iteratively. So at each iteration, step m, you can search for the parameters theta at this step that maximize the expected value of this logarithm of this probability with respect to that z. So we have x, that's our observed data. So these are my data points. And we have some latent data. So it's often, these data is often somehow intractable as it grows exponentially. And depending on that, you may want, well, you are trying to estimate somehow your parameters. So what we do in here, we perform two steps. So very similar to what we had in here. So basically the same thing, more or less, just a different point of view. So we perform a expectation step. So we calculate an expectation of something. In this case, our D can be probabilities of the point to be generated with some particular distribution from that distributions that we have, and some maximization step. So when we are finding the parameters of that distributions, that will maximize something for us. In this case, our expectation. Here is the E step, so expectation step. That's what we have in here. So we have our data set, we have our parameters, and that's probabilities for that Zi multiplied by logarithm of likelihood. We use the bias rule and we get this sort of formula. I know that looks a bit of complicated, but that's okay. So it's, in some sense, it's absolutely analogous to what we did previously, just like some sort of different point of view. And we have this sort of EM algorithm that, of course, that works quite similar, of course. So we have to initialize our parameters, we compute the log likelihood, and we find the posterior distribution of Z, and then the expected complete likelihood under this distribution of V. So when we have it, this P, ZX with some theta, this is basically our AIK. So the probability to belong to some distribution depending on the information that you have. So you have some data set, you have some parameters from the previous step, and you can guess based on that what are the probabilities. And then you calculate the next step's parameters. So here is some sort of picture. Well, I think I won't get into all of that troubles, but picture I should show you. This is a nice picture that should give you some intuitive ideas of what is happening. Here is, once again, here is my data set, these points. This is the step number 1. So at this step number 1, I have two normal distributions that were chosen by me, basically, somehow, I don't know, in some arbitrary way. And I don't know anything else except of this. But having these parameters of these distributions, I can calculate, once again, my AIK. Of course, if I suppose that parameters are these theta 0, so that my guessed parameters. These AIK, they define me how much each point belongs to each of the distributions. You see that with colors. So I have a red distribution, and these points are almost all red, so they strongly belong to the red distribution, while these are blue and they strongly belong to the blue distribution. And these, they have some intermediate color that signifies for you that these points are like a little bit in a blue distribution and a little bit in a red distribution. So something intermediate. And at the iteration number 1, when I had this AIK, I can perform this iteration and calculate my parameters theta. So you have seen that formulae, and I showed you that because we have very nice functions, the exponents, we can write some quite simple formulae that can be like, we can calculate that parameters just having AIK and of course our data set. So that was enough to update everything. And we can do that and we update everything. And you see here that we have a little bit different parameters for the both of the distributions. Having these new parameters, I can once again estimate my AIK. I can do that. And here I'm re-estimating them, and you see that these points are now belonging to the blue clusters, to the blue cluster much more than to the red cluster. Great, I have new AIK. I estimate my new parameters theta. Here I have them. And once again, I estimate my AIK. At some point, everything converges, and I get my result. Here are some more formulae like that expectation maximization. Of course, I don't want to get very deeply into that, so here is some expectation calculated, and here are the equations that I get at the end. Look quite complicated, so let it be that way. And when I have that thing, I can calculate the maximization step, so perform M step. I do all these derivatives to get my maximal values. And you might see in here that these formulae are absolutely the same that I showed you with the previous method. So that's basically just 2 points of view on the same thing. So you have the same formula for mu and for sigma and for pi. And that is quite natural, because why would you have some different formulae? They should converge to the same thing if the problem has a solution. So that's it. And with the same method, you can approach to k-means. And you can probably recall that I told you about k-means, that you can think about k-means like fitting some sort of normal distributions to your data. And that was quite similar to the mixture model that we have today. But I told you that there is some trick to that. So when I'm doing k-means, it differs from GMM in one aspect, in one quite interesting aspect. Does anyone recall what was that aspect or that property of k-means that makes it from one side similar to GMM, and on the other hand, it's the difference between k-means and GMM?
The fact that we do not know how many clusters we have?
No, not that. That's regarding parameters of the distributions. Do you recall the picture I showed you in 3D?
K-means uses some kind of distance, and GMM uses probabilities.
You can use probabilities for k-means as well. I showed you a picture with normal distributions.
I guess you mean that note you mentioned that k-means is somehow trying to fit a mixture of Gaussians, but those Gaussians are equal with equal parameters.
Yes, you have sigma equal for all that normal distributions. Of course, you cannot have all their parameters equal because that they will just overlap. But for a k-means, you consider normal distributions with the same matrix sigma, but different mean values.
Yeah, the means are definitely different, yeah.
If you are fixing that sigma value, of course, you make your model a little bit more stiff, and I showed you that it causes some troubles for k-means. So k-means is basically GMM, but you fix in a particular way your sigma matrix. For example, you can suppose that it's diagonal and has ones on the diagonal. So unitary matrix, why not? And that was the case for k-means. And here is an example. I am redoing k-means in here. So the same E and M steps, but here it's taken into consideration that all that normal distributions, they should have that equal sigmas. And all in all, I have this sort of equation. And you can recall probably this equation from the previous lecture. What we did in there. So we had aik, and we had our parameters mu k, and we were updating them continuously. One parameter, then another, one, then another. It's like, I don't know, it's like pouring water from one glass to another. So I'm always thinking about it like I'm having two glasses and I'm pouring water from one glass to another, then back, then another, then back, and so on. And it seems that these procedures, they converge and they give us some sort of result. Of course, not always do they converge, but which method will converge you in each case? Of course, it's the problem of minimization problems. Okay, and here is, once again, here I recall the Lloyd's k-means algorithm. So when the clusters k are initialized with these parameters mu k, and then we do that iterations like assign xn to the closest cluster with the cluster center mu k and re-estimate values of mu k, having that parameters, and of course check for convergence. So Lloyd's algorithm, you see that it's pretty equivalent to doing that GMM, but just you have fixed the parameter sigma. Okay, with that being said, I guess it's a nice place to stop for a moment and take a break. And then I will show you just a few more practical things. And I guess that will be all for today. Good. So a break. We have already considered some theoretical basics of the GMM. So we already know how awful do that formulas look like. And now I want to get to a quite small but some more practical part. How do we do that GMM in practice with sklearn, and what can we get out of that? So let's consider a few very simple examples. So here is the first one. I will remind you some caveats of k-means and show you some cases when GMM outperforms k-means. So here is an example when we generate some blobs of points and we are trying to perform some prediction with k-means. So I'm doing some fit and predict. Here it works quite nicely. Here is the explanation why it works nicely, because if I'm trying to fit some normal distributions and I have that sigma matrices diagonal, and you might see that these all blobs of points, they can be encircled. So I can draw some circles around them. All these circles have, let's say, equal radius. And this signifies to me that my normal distributions have diagonal matrices sigma with equal values on the diagonal. So you can think about it like a, let's say, some level of the normal distribution. So I'm like cutting my Gaussian and I'm getting a circle. But you might, of course, guess that this works not so nice and smoothly if I have my points somehow distorted. Here is another example. Once again, I have 4 clusters of points, but this time, when I'm trying to fit them into these sort of circles, I'm getting into some troubles. So I cannot separate these 2 clusters. They are like mixed together, and that, of course, makes me some problems. So I cannot deal with this sort of data set with k-means. It doesn't work that way. But of course, you might guess, if I have some more freedom in choosing my parameters, so I will use normal distributions with different sigmas, I can do something in this case as well. Let's give it a try. Here is my Gaussian mixture model. You can find that in sklearn mixture. Once again, you define the number of components that you want to have, and you perform fit and predict as expected. And here is an example for a more simple data set. So here I'm fitting 4 blobs of points that were correctly classified with the k-means. Here I'm trying to get some matrices out of there. So here is AIK, the probability membership or probability responsibilities. Well, depending which book you read, you might see different terms. And this is the measure. They measure our level of uncertainty. So each point, we can prescribe it to maybe different cluster, and these values, they show us how sure are we that this point belongs to some cluster. Here you see that most of the points were classified quite definitely, and that's great. Okay, so we can depict AIK with the size of the points at the scatter plot. So just take the maximum value, square it, and let it be the radius of the point. When point is close to the borderline, it's getting smaller. Okay, and here is an example that shows us how GMM works on these data sets. So here we have it. And now let's try it on the stretched data set. So here is another picture that shows you how GMM worked on the data set where these blobs are stretched. As you might recall, the k-means method was not able to handle this. We were trying to fit circles into there and to grab our points into a cluster with the circle. You cannot grab them with a circle. It doesn't work that way. Moreover, you should have all that circles to be equal. Here, you see that you can change parameters of your normal distributions. You have much more freedom to choose them, and you can grab your points with these sort of, let's say, ellipses. Okay. Here is one more example for you. This is called choosing the covariance type. As you might guess, in the previous example, I was minimizing all that functions with respect to all the parameters of my normal distributions, and I let them to be any, whatever to place, I can place in there any numbers. So the matrix sigma can be anything, the parameters mu can be anything, and so on. Well, sigma should be symmetric, but anyway. And now I want to pose some additional restriction. So that may be the case that in some cases, I may want to pose some additional restrictions on my parameters. And of course, the first one parameter that I might want to restrict will be this sigma. So this matrix sigma, depending on the situation, I may want to somehow restrict it. And I can do that. I have a very convenient parameter to make that. It's called covariance type. And let me show it in here. When I'm creating that Gaussian mixture, I define the number of components, and I can define the covariance type. And this covariance type can be either full. In this case, you might have any matrix sigma, so nothing is restricted. And here you see how it fits some blob of points. Or you can say that it is spherical. That means that your normal distribution is symmetric with respect to rotation. That restricts your sigma matrix. Or you might say that its type is diagonal. So you have a diagonal matrix, and you have, well, you may have some different numbers on that diagonal, but the off-diagonal components should be equal to 0. So here you see how that looks like. So depending on the situation, on whatever you want to have at the end of the day, you might have different pictures, and you may want to restrict your parameters. Well, are you restricting them, or to do that, or to do not, and so on? That basically depends on the problem that you are solving. So probably you might get some, I don't know, some ideas about the data that you have, some domain knowledge, let's say that, and basing on that domain knowledge, you can, well, think, do you need all the possible values for that sigma matrix, or you may want to restrict it somehow. Is it meaningful? Is it not meaningful? And so on. So that depends on the nature of data that you have. But what I want to emphasize that if you need that, you have the ability to perform that in sklearn in a quite convenient way, just setting some sort of parameter covariance type.
Will Gaussian mixture work with Mickey Mouse set of data, which from previous lecture?
Yes, it should work, and I guess maybe I have. No, I don't have that yet. That should work with that data, because now we have the ability to change our parameters in a way that we can fit our normal distributions to that data. But let's try to do that. Let's try to do that. Why not? Okay, so I'm trying to create some big blob in here, more or less, trying that to do more or less round. That will be the head of the Mickey Mouse. And let's give him some ears, yeah? So let's do something like this. And like this. Okay, so well, more or less probably looks like what we need. Let me do some first guesses, and let's try to clusterize that. And here is the result. So you may observe it with your own eyes. I'll be, well, I didn't try that. So this result is in some sense interesting for me as well, because I didn't try that. I have just implemented this sort of machinery in GS to show some examples, and I'm really happy that it didn't crash, for example. And now you see that it works. Here is how that works. So here is my main blob, and these are the ears of the Mickey Mouse. And you see that the right ear, it somehow happened that I have put these points a little bit further from the head of the Mickey Mouse, and it stabilized almost immediately. So the one step, second step, third, and here it stabilized more or less. While the, I don't know what's this color, it's not green, it's like cyan or whatever. There's a greenish color. We see that this blob needed more time to become let's say, more stable. And here is the 3D plot that we have. So here I started, and here's how it's going.
Okay.
Okay, so that's what we have. Yeah, so you're absolutely right. The data set that was quite problematic for the k-means, because we didn't have any ability to choose that distributions with different parameters. For example, in here, even if we have this sort of spherical distribution, I still can have different sigmas for different normal distributions, and I can still fit something into that Mickey Mouse. You see that normal distribution, they are almost symmetric. So I have something like this. It's quite restricted, let's say. And anyway, that still works, and still works better than the k-means that we had. So it has more freedom than the algorithm that we had previously. Okay. Here is another example. And you might guess that in this example, the GMM model will fail. So it's not like we can solve everything or every problem that we have in previous lecture with GMM. Something can be solved, something cannot be. And you might guess that if I have these half moons, these data set, I may want to have one of the moons or in, let's say, one cluster, and the other one I want to get in the other cluster. But of course, even with the covariance type full, I cannot cover each of these parts with one such thing, with one such ellipse. So if I'll be doing that guesses for the distribution functions, I will get that parameters, but I cannot fit all these points into one normal distribution. And here is an example how that works, and you see that we don't basically get what we want. So please remember that GMM is not some sort of snake style, and you can't expect it to work in each case that we had previously and that we have. Sometimes it works, sometimes it doesn't. But it still doesn't render GMM useless for this case. Please recall from the beginning of this lecture, I told you that GMM, yes, we use it for clusterization. We can do that. That's okay. But its primary goal is a bit different. Which one it is? Do you recall?
Probably to make first estimations for future classification methods.
So what is the, let's say what is this model? So this is a generative model. So its primary goal is to estimate some sort of distribution behind our data sets, and having this distribution, we can generate some more points. And that will be okay. And we can still, for these sort of data sets, we can still generate some distribution and still add some more points with our generative model. And here is an example for you. So here you see that I have taken a lot of normal distributions, and I'm trying to fit these points not into two, but into many normal distributions. Yes, this renders this sort of situation useless for the purpose of clusterization. I don't want to clusterize this into 10 or 20 clusters. Yes, that is quite useless. But I still can cover these points with some sort of normal distributions, and with the help of the parameters, getting the parameters of that distribution, I can use them further to generate some more points. And here is an example of generating some more points. So this was the original data set. That's what I have. And this is my new generated data set. So I have estimated the parameters of that normal distributions, and I was able to generate me some new points. So please remember that, first of all, this is a generative model. I will show you an example of that generation in a moment, but there is one more thing that we need to consider before getting to a practical example. Please recall that we always had some problem of getting some, I don't know, some number of components. So we have these troubles with k-means, and of course, you might guess that we have the problem of estimating the number of components for GMM. So how do we find that number of components? That depends on the situation, but I want to show you at least few cases how to do that, and let's say few methods how to do that. So the first method, of course, is cross-validation. Cross-validation is suitable for almost anything that you might think about. So if you have some problem, you can always try, I don't know, to guess some parameter, go with it up to an end, and then just estimate how good is your result. If your result is good enough, that's okay. If not, then not. So not wasting some more time on that. The other one approach is to estimate so-called Ekaike information criterion. So we have AIC, this criterion. It's some sort of an estimator of out-of-sample prediction error, and thereby relative quality of statistical models for a given set of data. Given a collection of models for the data, AIC estimates the quality of each model relative to each of the other models, and thus provides some means for model selection. So we can estimate how good is each of our models and then select one of them. And suppose you have a statistical model of some data. Let K be the number of estimated parameters in the model. In our case, we will have normal distributions. Each of them has some sort of mean value, has a sigma, so on and so forth. So there is a bunch of numbers that you will estimate, and you can basically calculate the how many numbers do you have. And let L be the maximum value of the likelihood function for the model. And then this AIC is calculated as follows. So 2 times K minus 2 times logarithm of L. So we have some likelihood function, we have this thing, and we can calculate that. That may look a little bit, I don't know, maybe strange for you. But the thing is that when we are performing all these estimations, please recall that the models that we are comparing, they have different number of parameters. So when I'm taking different number, I know, of clusters, for each cluster, I get some additional parameters, some additional mean values, some sigmas, so on and so forth. So each of them has some sort of, and they all have more and more parameters. Of course, you might guess that having more and more parameters, it gets more and more easy to feed the data. But it doesn't mean that our model gets better. If I have, I don't know, a cluster for each point of my data set, I can clusterize that perfectly. I will just set each center of the cluster equal to the value of the data point, and that's all. And I have, I don't know, some zero error. Looks very nice in numbers, but it doesn't work. So it's not the clusterization that I want. Probably I don't want clusters that contain one point only. So please recall that comparing models with different number of parameters, it has some troubles to it, because giving the model more parameters make it look better, but it doesn't mean that that model is better, because it may be just overfeeding your data. And that's why we have all these parameters. And you see in here that these criterion AIC, I will look for some sort of minimal value for it, and giving the model more and more and more parameters make it look worse. And that's exactly what I want. So I don't want model with many parameters. And of course, these criterion should find somehow some balance. So when my model performs very poorly, that should be the case that I don't take that model because it's too bad. But when my model makes everything look very nice, but it has too many parameters, I should stop that as well somehow. And this is the criterion. And criterion number 2, that's the Bayesian information criterion. Here I have links for you, so you can check, for example, some Wikipedia for more details. But the same idea behind that. Here is an additional parameter number n, that's the number of data points, so size of the sample. And of course, you have k number of parameters estimated by the model, and so on and so forth. So here it is. Here is the plot for you. I have this data set with half moons, so this one. So this is the data set. And I'm trying to estimate BIC and AIC for this data set with my Gaussian mixture models. So here how it's done. So I have my GMM, n is the number of components. So I'm trying different number of components, starting with 1 component and up to 21 component. And I'm trying to perform that GMM. And here I'm trying to plot the data number of components versus BIC or AIC. And you see that I can quite easily get that data from my GMM just by calling the appropriate functions. So you don't need to write that on your own or something like that. You have everything in there in sklearn, so just use it. That will work quite nicely for you. And here are my 2 plots. And looking at these 2 plots, at BIC and AIC, I can search for their minimum, and finding that minimum will give me some information on how many components do I need to take to make my GMM work more or less nicely. Please remember, the number of components measures how well GMM works as a density estimator, not how well it works as a clustering algorithm. So taking into account all these criteria like BAC, AIC, so on and so forth, I will get some information how good is my generative model, so how good will GMM generate some data for me, but not how good will it clusterize. So please remember, these are 2 different problems. For these half moons, of course, here are 2 components. But if you want to use some sort of generation with GMM, you need much more components to cover this data set. Okay, now the last example for today. Let's generate some new data with GMM. We use our data set that we all know and love. That's MNIST digits. So here is my data set. Here how it looks like. And what do I want to do with that? First of all, there are too many dimensions. You recall that in MNIST we have small pictures. Each is, I guess, 8 by 8. So if I consider each of these pictures as a point in some multi-dimensional space, I expect that space to have 64 dimensions. That's quite many. So first, let's do some PCA. So very simple, we are doing just some PCA, and we are trying to transform that to keep, I don't know, 99% of the variance. Hopefully you remember what this method does and what it means to keep 99% of the variance. Now I use AIC to choose the number of the normal distributions that I will use when creating my generative model. Here are my model. I'm trying n in a range from, I guess, 50 to 210. And I'm doing that with some step because it takes a bit of time, all these calculations. But all in all, I get some plot of AI CS, and I can look at this plot and guess how many do I need. So here it looks like that maybe 110 will be good enough. Now I'm feeding this data. I see that my GMM converged. That's okay. And now I can do some inverse. I can generate some data with this model. So what it does for me, it generates me a sample of 100 points in some multidimensional space. Of course, you recall that I have removed part of dimensions with PCA, so now I should perform an inverse transform to return back to the 64-dimensional space, and here I'm trying to plot them. And that's what I have. They look like numbers. So let me draw that on the board. I just want you to feel what happens, so what we are doing to get all these numbers. Okay, so here is my data set. So these are some pictures. Here are some numbers, and I have all these pictures 8 by 8. I consider them as the points in a 64-dimensional space. Now what we are doing with that? We are performing PCA. It changes the dimensionality of the space. I don't actually know exactly which will be the new dimensionality because I have restrained the percent of explained variance. I don't know, it will be some smaller number. Let's say, for example, I don't know, 31. So I get some points in here. Okay, now I'm putting all these points into the GMM. So I want to train on these points. I'm training my GMM to get some parameters. So I'm doing some training. Here is my GMM model. And what I get in here are the probabilities pi 1, for example, pi 2, pi, I don't know, k. And I get parameters of my normal distributions that I have in here. So in each of these boxes, I have some normal distribution. And they all have different parameters. They all have different parameters. I get them from training. I train on these points. Now I can ask this model, when I have everything this, I can ask it, I can say it, generate. So I can ask generate. some random distribution of these all will be chosen and will generate me a point. So any of them will give me some point in some smaller dimensional space with, let's say I have arbitrarily chosen 31 dimensions. So I will get some points in here. Now I will perform the inverse PCA. Let's call it PCA to the -1. And of course, I can use the same parameters that I have in here. So PCA, that's machine learning method. It's trained, so it has trained somehow. So these PCAs are linked. I perform the inverse of exactly this one PCA. That returns me to the 64-dimensional space. And now these points can be treated as images 8 by 8. So I can get from here, this was my original data set. I can treat that as images and say that here is my generated data set. So some more images. And what is interesting in here, if you look at this picture, you see that there is no step in here where the machine knows that you want numbers. It doesn't understand the meaning of the pictures that we have in MNIST. We didn't tell that anywhere to the machine. So in this scheme, there is nowhere told anything about the meaning of these things. It doesn't even know that these are pictures. It can be anything. So any point in the 64-dimensional space. So when we have converted them into these points, we have forgotten about all the internal structure of these images that we have. And what we are expecting, that this internal structure, it can be somehow seen in that multi-dimensional space, and we can find some probability distributions together with, well, probabilities to work with them, that we can mix a model, so we can find some overall mixture model that more or less models this thing. So the distribution of these points. And of course, we might think maybe if we are lucky enough, if everything works fine, we can expect that the result that we generate will contain something that looks like numbers. Some number 2, number 3, and so on. So that's the interesting part. It's not very interesting if you, I don't know, if you recognize these numbers and then you can just draw them as you wish. It's not so interesting. But the interesting part is that you don't tell anything about the meaning of all these things. So machine does not know anything about the internal structure of our data, but we want it to guess that internal structure somehow and generate us more data that looks like what we had at the beginning. So this is the interesting part. And now let's look what we have. Here are the newly generated digits. And looking at them, you might probably guess that it worked more or less fine. Yeah, we can see there are some sort of smears in here, so they are not so clear as the data set we have started with. But anyway, this one, okay, to the left or to the right of the page? This one. Yeah, that looks really something like that. But on the other hand, many numbers are more or less recognizable. So some of them I can recognize like 4 or like 5, 3. So some are quite strange. Some are more or less recognizable. Well, you can recall, for example, some methods like neural networks that can generate some images. Yeah, so some generative models as well. But with the neural networks, you can recall that sometimes they generate quite strange images as well. Some, I don't know, additional fingers and hands, some other things. So this is not an exception, of course, taking into account that GMM is much more simple method than whatever we have there. But the general idea is basically the same. So that's what we have. Okay. What now? Well, it's almost everything I wanted to tell you. Here is just some demo for you, the last one, I guess, for today. Hopefully that starts. And I will just show you how this method works when you are dealing with the GMM from sklearn. Probably you can play around with it. I don't know, let's try some case, I don't know, some big cluster, some small cluster, let it be here somewhere, and let me do the GMM.
Probably should increase number of clusters.
Yeah, so we can change the number of clusters. So here it's with the 1 cluster. It doesn't look very well. Let's try, for example, 2 clusters. That works much better. So these are the result from the sklearn. And here is maybe the most interesting part for you of this example, because drawing that's drawing. But this is how to get the parameters from the GMM that we have in sklearn. Here I'm performing that. I'm setting the number of components. I'm setting the type of covariance. Of course, you can change everything that performing fitting. And here you see how do I get centers. So you have parameter means. How do I get covariances? Because probably you may want to do something with that normal distributions on your own. Why not? These weights W, these are the probabilities of choosing one of that normal distributions. That's what I called pi in all my equations. So these are pi's, these are sigmas, and these are mu's. And of course, you can do something with that on your own. So that's the way to get parameters out of the distribution. You can use this demo to play around, to try different, let's say, data sets, to arrange your points differently, to get basically some intuitive idea how the GMM works. Okay, with that being said, I guess we are more or less done for today. So just as the recap, so what did we do today? We considered a method, a generative model, GMM. I guess we saw some generative models before, but anyway, this is quite nice one. So we have considered this model. We saw that we can use GMM for both clusterization and for generating new points. But as a generative model, it's much better. So it's not like, it's maybe not very recommended to use that for clusterization, but for generating new points, so that can be a very nice model. we saw that some cases in practice can be really thought as a mixture model. So for example, if you recall the height of people, or I don't know, some velocities of particles, if you have different kinds of particles and so on and so forth, you can think about them like some mixture models. And maybe you can use that somewhere in practice. For example, if you don't have enough information, you have detected some particle, you have measured its speed, but you don't know what is this particle, what's that. You might probably guess if you have different kinds of them and each of them has different distribution, you can at least estimate some probability of this particle to be that one or that one or that one. That's good. And we saw that we can generate some new points with the GMM. And the most interesting part was that I have taken the data set that contains numbers, and my model does not know anything about numbers. It doesn't know what is that, how are numbers grown or something like that. But when putting that into the model, it is able to learn more or less good to draw some numbers. And that's really, really interesting. Of course, if you will, in the future, maybe you will work with some sort of more complicated models, some neural networks and so on, and you'll be able to get much better results from them just because that models are much more complicated. But anyway, this one paves the way for understanding how everything works. And I guess with that being said, if you have maybe any questions or comments, please. Well, if not, then have a nice weekend and see you next Friday.